I want to prove a result related to phi of a prime power. P represents a prime number right here, and then k is just a positive integer. Okay, so let's work with an example of something like that, namely 25. Now I'm keeping this small, but notice that this is 5 squared, so it is a prime number squared. Now I'm going to go ahead and write the answer and just explain why the answer is what it is. Okay, the answer is 20. And what this really means, folks, is there's 20 numbers less than or equal to 25. Positive integers less than or equal to 25 that are relatively prime or coprime to 25. That is, they have no common factors with 25. Now, notice that this is 5 squared. Now, this is not too hard to see if you just consider the possibilities 5, the multiples of 5, 10, 15, 20, and 25 itself. So these numbers respectively would, if you phi at 25 and 5 would have a common factor of 5. Phi of 25 and 10 would have a common factor of 5. And now they wouldn't be relatively prime, right? So these 5 numbers are not relatively prime to 25, so they have to be subtracted from 25. That is, this is the same thing as 25 minus 5. Okay, now there's 5's kind of getting overused in a manner of speaking here, but there's 25 numbers less than or equal to 25, right? And exactly 5 of them are not coprime to 25. The other 20 would be coprime just based on the fact that 5 is a prime number, okay? So we want to show in general that this is true, and you can see that this gets it done for, you would have 4 times 5, which is 20 right here, right? But we want to show this in general. Now, I'm going to just state this claim. I'm not going to go to too much trouble to prove it because I think it's very clear. If n is a multiple of p, then it has to be, the greatest common divisor has to be greater than 1. A lot of the times it's 5 or some other power of 5 or of p, but it's going to be greater than 1, which is all that's important. It says that p to the k and n are not coprime, right? Now, otherwise, if n is not a multiple of p, it's the p of k and n are always relatively prime, and that's kind of was illustrated up here. I didn't list all the possibilities, but these are the only 2 possibilities, and so I'm not going to try to prove this claim. Hopefully, I think it's fairly self-evident. Okay, now let's keep going. Now, so because we're interested in the number of multiple of p's that we want to subtract away from p to the k, we get this result right here that involves a floor function. Okay, we know there are p to the k minus 1 multiples of p less than p to the k. Now, if you may not think the floor function is necessary here, but let me just give you a concrete example again. What if you had, let's say, 22, the floor of 22 over 4? Okay. Now, notice that this is equal to 5. But what is that? That is exactly the number of multiples of 4, okay, that are less than or equal to 22. Namely, I can start. This isn't too much trouble to write out. 4, 8, 12, 16, and 20, right? So the floor function is more useful when you're talking about a fraction, but it still gives you the number of multiples of 4 that are less than 22. And in general, if you have a over b, it's the number of multiples of b that are less than a. Okay? But notice there are 5 right here. 1, 2, 3, 4, 5 multiples of 4. Okay? So this floor function looks superfluous, but it was useful. So we know now that there are p to the k minus 1 multiples of p less than p to the k. Now, a lot of you might just say, oh, it's obvious, and go with it, and I understand that, but this is just kind of a formal way to do it, all right? So what we get right here is that phi of p to the k is equal to p to the k minus p to the k raised to the power of k minus 1 based on this result. This is kind of the meat of the proof, if you want to call it that. Now notice we can factor out a p to the k minus 1, so you get p to the k minus 1 here as the greatest common factor times p minus 1. Okay, folks, and again, this is what we were trying to prove. Remember, we were trying to show that phi of p of k was p minus 1 times p to the k minus 1. This one example suggested this might be true. Okay, but you can, what we looked at right here is quite similar to what really happened here in the general case, where p is a prime and k has to be. And y'all, by the way, k would have to be an integer greater than or equal to 1, right? And of course, p is a prime. So y'all, that I guess that proves it. So I guess at this point you can write QED. So it's a nice, I would call it a fairly rudimentary combinatorics problem. You take all of the numbers, and from that number, you subtract all the numbers that are not possibly relatively prime. There's no way that they're relatively prime. And so anyway, that's the end of the proof, folks. Thanks for viewing.